Okay, so we're now going to take the divergence of a given vector field. Now, first, the divergence of any vector field is a dot product of the nabla operator dotted with the vector field. And this, in turn, gives us the partial derivatives in the x, y, and z direction. But notice there is no vector here, which makes sense because we're taking a dot product, which converts two vectors into a scalar. Similarly to how we perform derivatives on gradients, we will do the same method where we will find the partial derivative in each direction and combine them. First, the partial derivative of f with respect to x is going to be, or in the direction of x, is just going to be 2x. The partial derivative with respect to y is going to be e to the x, e to the xy times x. Or, sorry, I'm going to write it this way. X e to the xy. The partial derivative with respect to z is going to be in the direction of, is going to be cosine of z. Now, you might be wondering why I didn't bother to compute the partial derivative of every other vector concerning this. And it goes back to properties of dot product. Now, AX is, if we are to draw a coordinate space in the X, Y, and Z, so this is Z, X, and Y, what AX means is a basis vector in the direction of X. What AY means is a basis vector in the Y direction, and what AZ means is a basis vector in the Z direction. The dot product is concerned with asking about the dot product between two vectors, A and B, is their magnitude times cosine of theta. Now, if you notice, these three vectors are 90 degrees away from each other. And as such, cosine of 90 degrees becomes 0. So regarding this, what this tells us is that the only time we're able to take a partial derivative is in the direction that we only care about. So in other words, partial f, partial x, we're only acting on in the x direction. Similarly, for y, we're acting in the y direction, and similarly, z, we're acting in the z direction. As such, this leads to the following property. AX dotted AY is the same as AX dotted AZ. Oh, sorry. AZ. And it's the same as AY dotted with AZ, given that they're all 0, basically. So that's why, if you were wondering at any point why we only compute the partial derivative in that direction, it's mainly because of how it relates to the dot product and the properties of the dot product. Now, we computed our partial derivative in each respective direction, and now we're going to put it all together. So the divergence of the vector field is going to be equal to 2x for partial f partial y plus x e to the xy from partial f partial z plus cosine of z. And that gives us our following divergence. Now, whether or not we can really say that this divergence is sourcing or sinking, we can't tell until we plug in a specific point. So let's say we plug in a specific point. Let's say the point was 1, 1, 1. So we have the divergence of f at the point at point. And we get the following. 2 times 1 plus 1 e to the 1 times 1 plus cosine of 1. Now, at this point, at point 1, 1, 1, and this is an arbitrarily chosen point, we can see that the divergence, looking at term by term, is going to be greater than 0. So as such, this point is a source point, or I should say sourcing. And we can repeat this for negative points to see if it's sinking, to see if it's divergenceless. And, we can see just how generally the vector field flows from whether in or out of a sink or source. Next time, we're going to then be discussing about the third operation, which is curl. And curl only works for another vector. It will not work for a scalar. All right, thank you.